recent literature, because the work I present here, the experimental work, was already from a few years ago. So it was done with help of some PhD students. So Viju Pansi actually graduated in 2016, wrote a nice thesis. Artem Nikitin watching, and then I have Mark Salas, PhD student, working with me on this topic. Crystals from Donacharian and Wang Ying Kai in our lab. And then also to acknowledge long-standing collaboration with Takashi Naka from NIMS for high pressure experiments and Alex Amato and colleagues for MUSAR experiments. So I will use one slide to tell you what a topological superconductor is according, well, for me, why it is an interesting system. And there are a number of very interesting review papers, in particular just one of Sato and Ando. The first one I would recommend if you are interested in the topics. It's a nice mix of experiment and theory. So very briefly then, if we have a superconductor, of course, we have the pairing of two electrons, spin up and spin down, and we make a Cooper pair, and then we have the superconducting gap. And the excitation of the particles are given by, well, you have to use this Hamiltonian, the Gen Hamiltonian, and you get the Broglie bonds, and these are the elementary excitations. So this is a linear combination of electrons and holes. Now in a topological superconductor, a 3D topological superconductor, you also have a bulk gap, a superconducting gap, and also have excitations in the gap, or actually these excitations are only on the surface, that's important. And if you see here at zero energy, that is the Majorana-Fermion bound state. And so that is, I took this from a slide from Ando already quite a while ago. So actually we're after a system where you could have bulk superconductivity, topological states on the surface, and these would then harbor these Majorana states. Okay, let me then come to bismuth 2 selenium 3 intercalated. There are three of these materials, the copper, strontium, and helium doped, and the TCs are all in the order of 3 Kelvin. So let's first have a look at the crystal structure. So we have these quintuple blocks of selenium, bismuth, selenium, bismuth, selenium. And these quintuple blocks are bonded together by van der Waals forces. And the idea is that the strontium, indicated here by these pink atoms, that intercalates into the van der Waals gaps. This picture is actually taken from a paper by the group of Cava, where they actually made a similar picture for copper intercalation. Important, the space group is R-3m, so this is a trigonal material, and we have a C3 rotational symmetry. Superconductivity was discovered by Liu et al., reported in 2015. Resistance is just a metallic. Here is the superconducting transition at about 2.5 Kelvin for this particular sample. The idea is if you make this material and you add strontium, it's supposed to intercalate and you get superconductivity. If you make a kind of a composition where you would dope on the strontium on the bismuth sides, it is not superconducting. So this is also a low carrier concentration system. And then here are some magnetic data also from the same group. And actually you have reasonable shielding fractions, and also field-cooled signal is quite big, as shown here. So this could actually indicate that this is a nice bulk superconductor. Then, of course, we are interested in the topological properties of the materials. So one can do RPES. Here are data at 30 Kelvin. This is for a doped system. Here you see the Dirac cone. So this is the pure bismuth 2 selenium 3. Well, here you see only the surface states. If you would use a different energy, you would also see the bulk states. If you dope, or you intercalate, so 0.06, and here higher dopings, then the Dirac point shifts. So it is still, when you put the strontium in there, it is still, that has the topological surface states. Then there was a report about the upper critical field a number of years ago. And this group by Shruti, they measured upcritical field. This is a layered material, so you can put the field in the plane, and that should be isotropic, or you can put a perpendicular to the layer. So that's what they did. And here are the data. Maybe not so particularly interesting. And you can, of course, then fit this with some here linearized Ginzburg-Landau model, and you can extract some parameters for the superconducting state. Well, we thought we can actually do this better. So we actually prepared this crystal. We can also measure in this temperature range, because this was only down to about 2.2 Kelvin. So now I come to the study of the upper critical field. And actually, it's a fairly simple experiment. So we just have a slab, a flat sample. The z-axis is perpendicular to the sample surface. We put the current along the a-axis, and you can also define the A* axis here. So that is actually the axis which is at right angles to A and C in the plane. But normally you're only interested for a field direction in the z-axis and a direction in the plane. So here actually we measured all three directions, and then we had a surprise. You see here, if you apply the fields along the a-axis, so this is on a sample with 0.10, and this is about the superconducting transition. Here you need 3.6 Tesla to suppress the superconductivity to about 1.8 Kelvin. But for the other two directions, so you have a much lower field, only 0.7 Tesla. So if you plot the upper critical field, it looks like this. And this is surprising, because you would expect that A star give the same result. But here you see that A is much bigger than A star and C. So we said, okay, that's one sample. So let's look to a sample. So we made a sample with X is 0.15, and we measured also down to much lower temperatures, and we find the same. And actually we find a very large anisotropy between E and A star. So this is 8 Tesla, and this is like 3 Tesla. So this is really a large effect. Then we said we have to study this better. So let's also look then to the angular dependence. Put our sample on a rotator and directly measure how this critical field varies with the angle. Now, from the plane to C, we know that is normally it is smaller to bigger, but we also did a rotation for the field in the plane. So we rotate the field like here in the plane. So
why do you expect A star and A to be the same?
Because of symmetry. It's just for all superconductors, it's always the same if you have a one component order parameter. I will come to that towards the end in the presentation. Yeah. Yeah, for a hexagonal system, it is predicted to be isotropic, the critical field for a field in the plane. Also for a trigonal system. So we did the experiment. So we put a small field on the sample, 0.4 Tesla. And then we change the temperatures, and then we rotate the sample. So here is the field along A star. So here is superconductivity, here is the normal state. And then we change the temperature here. And for instance, if you sit at an intermediate temperature, you see here you're almost normal, this pink curve, and then it goes down and up again. So here we are completely superconducting. It means for this direction, the upper critical field is large, and for this it is small. But now, strange point here, of course, is that we would have expected that it would be 60 degrees or 120 degrees, but a twofold symmetry. And so that's really strange. That's really a puzzle. And that's obvious also if you plot the same data in a polar plot like this. So it's this the same data, but then plotted in a polar plot. This is for a current in the plane. I also come to that in a moment. Okay, so then we can directly plot the upper critical field. So this is also from in situ rotation. So this is for X is 0.10, and it looks like this. And this is also in the helium-3 system. So we find actually we reproduce what I mentioned on the one of the earlier slides. But here you see the whole angular dependence. So the same for crystals and twofold. So why do we have this twofold anisotropy in the basal plane? So that's the important question. Now there can be, of course, a number of kind of maybe ordinary reasons, or so you could have a structural transition. So we check that. So this crystal stays the same. It's trigonal down to low temperatures. You could have an in-plane anisotropy of the effective mass. because the upper critical field is related to the coherence length, is related to the effective mass. But this effect is very large in the upper critical field. And there are quantum oscillation data on bismuth selenium 3 with the field changing in the plane, and the anisotropy of the effective mass is really very small. So it cannot be due to anisotropic effective mass. Now, one point, and that is also maybe relates to the question, is that here we actually have the current in plane. And so if we rotate the sample, we actually also rotate the current, so we naturally break the symmetry. And particularly you can have an active flux flow, because if the current and the field are parallel, you have no flux flow, and if they're perpendicular, you could have flux flow. Well, we can already argue from our data that that's not important, but we also did an experiment where we have the current flow along the z-axis, and then we rotate in the plane, and then you can actually really take this effect out. So it is not due to these effects. Moreover, we did the same experiment under high pressure and up to pressures of 25 kilobar, and the effect remains there. So it seems to be really robust. So we really have broken rotational symmetry. And so we have to explain that. So we have to go to the theory. But there's one point that I want to stress, that we do not exactly know where the strontium atoms sit. And in our first paper, we also argued that maybe if there is some stripiness of these strontium atoms, you could have a lower dimensionality. And there are some indications that you have these things, but there are some indications for defects in these materials. Yes? Good point. There is a group that also reported anisotropy in the normal state, but very, very small. Well, this effect has been confirmed quite rapidly by several other groups. I will not go into details, but like the twoorbital, that was z-axis resistivity, then also in the argon group, by also Sakakiba in Tokyo, actually exactly the same data as we obtained. Kunchevich, so it's actually confirmed by on several continents. So I think that is that's good. Now I want to go to the theory, and actually there are a number of papers already before this work was reported that actually allude to this situation, that you could have this rotational isotropy breaking, and that you have special Cooper pairs, and in particular that were papers that were actually trying to explain properties of copper bismuth selenium 3, but exactly the same for strontium. So an important ingredient there is a model by Fu and Berg, and actually they use a so-called two-orbital model, where you have actually the bands are due to the two orbitals of the selenium PZ orbital. So remember you had the van der Waals gaps, and you have the PZ orbitals sticking into these gaps, and they would form a kind of pairing potential. And if you do the symmetry analysis, so group symmetry, where you have inversion, rotation, and reflection, so you have actually three one-dimensional representations like here, and you have one two-dimensional representation. Now, in the first work, also on the copper bismuth selenium 3, Fu and Berg actually posed that this would be the state, which is relevant here. So this is the delta 2 states, which is selenium atoms of PZ orbitals in this spin up and spin down in a linear combination with spin down and spin up. So that is this. This is like the LZ equal component in the triplet state. So we have 4 different states. So they go under the name delta 1 to delta 4. This is the singlet state, and this is in special states, which is a 2-component order parameter. Now, if you then continue and do Ginzburg-Landau theory to explain the upper critical field, you cannot get this result of this anisotropy by using a single component order parameter. So you need 2 components. And so you need this particular EU or E2U order parameter. And that's an order parameter that also has been proposed for uranium platinum 3, for instance. Okay, so then the Ginzburg-Landau theory that's worked out by Van der Bos and colleagues. Actually, it was also done by Krotkov and Miniev in the context of uranium platinum 3. And then the statement there is, if you have a single component order parameter, and for all the different symmetries, whether it's trigonal, tetragonal, or hexagonal, the basal plane should be isotropic. So no anisotropy. That was also found for uranium platinum 3, which is a hexagonal system. But if you have a two-component order parameter, like this one, so this is like a linear combination of two equal spin pairing states, then in the tetragonal symmetry, you would get a 4-fold anisotropy. Hexagonal uranium platinum 3 still isotropic, but if you have a trigonal symmetry, then the basal plane can have 6-fold anisotropy. So it looks like this. And so then you can have an anisotropy of the upper critical field. So when you take the field in the plane, you get this. But that's not what we observe. So that's now the difficulty. What we observe is more something like this. And so it is like 2-fold. And in order to come to this 2 anisotropy, you have to use some additional rotational you have additional rotational symmetry breaking. So the idea is that actually you would have 3 domains, but because of some mechanism, you break the symmetry and you have only 1 domain. But you could have 3 in principle. Now we can do one step further, and we can go back to the EU representation and write this pairing potential as this. So now we write it as a vector here, and there are these 2 components, eta x and eta y, and they were actually given the name by Liang Fu as the nematic order parameter. And then the idea is that that could point in 3 directions, but apparently the crystal selects only one of these directions, and that is maybe due to strain or structural disorder. And so you get this picture. So it is actually borrowed from liquid crystals, where you have these cigar molecules. If isotropic, then you have an isotropic gap. Here they are aligned along a certain direction, and your gap also has some anisotropy, and that gap is kind of pinned to the lattice, possibly because of strain. You can also make predictions then for the superconducting gaps. If this director is along the x direction, you would have 2 gap nodes in the y direction, and if it is along the y direction, you would have 2 gap minima. So you can try to look for these as signatures of these different delta 4x and delta 4y superconducting gap functions. Now this is about the strontium doped case, but in fact, actually very similar phenomena have been reported for the copper doped case from NMR. I have not time to go into details here. Also 2-fold anisotropy. So here you directly measure the Cooper pair spin moment. Also in the specific heat of this material, and also in the upper critical field. And also for the niobium case from torque measurements, there is evidence for a 2-fold symmetry. Now, in the remaining time, I want to make contact to the recent literature. And I will do that for 3 different materials. So I will go through some recent results without discussing that in too much detail. Thank you. Doing that in too much detail. First, about bulk superconductivity. It is an issue. We tried very hard to measure the specific heat anomaly at the superconducting transition in the strontium bismuth selenium 3, but it appears that the gamma value is so small. It is somewhere below maybe 0.3 millijoule per mole Kelvin squared. So we have not enough resolution to see the specific heat. So you have to use a better technique. That was done in the Argon groups. They used microcalorimetry, and here they see a beautiful transition in a specific heat. So this indicates if you have these tiny crystals that they can be bulk superconductors. That was also confirmed by Sakakibara again in Tokyo, 2-fold anisotropy in the specific heat. But they also find some, referring to the question of Xima, some anisotropy above the critical temperature. Now, another course, very interesting experiment you can do this. You can try to strain your material and see whether you can make it maybe more monodomain, or maybe you can make 3 domains. That has been done by the Kyoto group. And so this is actually the first result. It's recently reported. Here is some anisotropy of the critical field. And if you get 0 strain, and if you strain, you see that it is more elongated in one direction. So they claim that they can link the strain to this effect. Then X-ray diffraction indicates that there is some crystal inhomogeneity, in the sense that the C-axis in the crystal seems to wobble around a little bit. So these are, so you have some kind of I would not call it grain boundaries, but you have smaller crystallites. And from transmission electron microscopy, also for this material, it's clear that not all the atoms are intercalated. So,
question. So
yes.
The first one for the calorimetry, is that transit within the superconducting state? Or?
Yeah, the transition is 3 Kelvin. Yeah, so that is just the.
Is it at the same point where you go superconducting?
Yes.
Within the state. Okay.
Yeah. That's just the superconducting. That's a BCS superconducting transition. But they don't know the gamma value for this exactly. But from this claim, they claim it's bulk superconductivity.
So the anisotropy develops at the same point with the superconductivity.
Oh, sorry. If you think about this in this experiment, sorry, yeah, this is very small. I have a larger view graph as well. But here it depends on the field. I think if they make a larger field, it still persists in the normal state. Yeah. For copper bismuth 2 selenium 3, well, there are a number of interesting experiments have been done. I mentioned already the NMR, the night shift, very interesting. Also specific heat. A very interesting experiment is STM. Here are vortices, and you see these vortices are elongated along a certain direction. And this is in the field of 0.2 Tesla. So this also seems to indicate that there is some twofold anisotropy for these vortices. This material has been very much investigated as regards to the structural properties, and you can have all type of maybe problems with these samples, but if you prepare them by electrochemical intercalation, as was done by Joshi Ando, you get really good samples with about 60% superconducting volume fraction. Speaking about then zero bias conductance peaks, that was also done by Ando, and they claim that they have some peak in the gap, and they claim it's a Majorana-Fermion state, but nobody will believe that, I think. So now let me conclude then with niobium bismuth 2 selenium 3. Their thermal expansion experiments have been performed, and they claim that there is what they call vestigial nematic order. So this is the field, this is the length change, here's the superconducting region, but that above the superconducting state, there is already some breaking of the symmetry here. There's something which, yeah. So, but that has not been confirmed by other groups. However, a very interesting experiment was done by Kamiga, which in synchrotron radiation. They looked very careful to the structure of this niobium intercalated bismuth 2 selenium 3, and they found that depending on how you prepare the sample, but there's a fairly large amount can be present of a misfit phase. The misfit phase, that is this one here, and that's also superconducting on itself. And so here are X-ray diffraction peaks. This is for the misfit phase. No, this is for the misfit phase. This is for the bismuth selenium 3. If these are different sample concentration, strontium concentrations, if this is large, you have lots of this, and you also have a large superconducting volume fraction. So here's a very clear link that actually it is actually the misfit phase actually which determines the physics in the niobium doped case. So here's my summary. Yeah, well, you can read it yourself. I want to stress that, well, as regards pressing questions, so where are the doped atoms? So that's still an issue. So why is there this spinning of this nematic director? Probably strain. So can we have superconducting domains? And I did not address this, but there is also some X theory which tells you where you could find the Majorana zero modes, which are here, for instance, in the gap. So I have a slide about that if you want to ask me. Before closing, I want to just make very briefly publicity for the strongly correlated electron conference in Amsterdam. We are currently organizing it. It's the last week of July, and we plan on an in-person conference. So I think that that should work out. Yeah, so it's end of July, and we have already a website, and I think the abstract submission will open about half January. Okay, I will leave then the summary on the screen, and let me thank you very much for your attention.
Just a quick one. So I remember in the context of copper doped bismuth selenide, the claim was that the superconducting volume fraction was very low, like 65% or something.
Yes, maximum 60%.
60%. And when you tunnel into the surface, like very little of the surface actually shows any signs that the material is actually superconducting. Is it better in niobium and strontium doped?
Niobium, certainly there are samples, but maybe because of this misfit phase contribution. Well, there's a very nice transition also in the specific heat. And for the copper doped case, it is never, there's also always a larger residual gamma value. But for niobium, you can have better superconductivity. Absolutely, yeah.
So, two questions. First one, quick. Maybe you said it, but if you warm up and cool down, you get exactly the same thing again, right? This director is the same. Is that right?
A good point. Of course, we did that for our samples, and that holds. Yeah, that's true. Yeah.
So second, and maybe this is more of a theoretical question, but it certainly relates to the data. The conclusions about necessity of two-component order parameter, this assumes that the normalcy is completely isotropic, right?
Yes.
So if you have maybe you have indeed some structure of the dopant atoms, and this is giving anisotropy in the normal state, this can be inherited by the superconducting state with just one single component order parameter in this regard. Isn't that true? So if I have an isotropic normal state, then a lot of these kind of conclusions about things being more exotic here don't follow.
Yeah, but then you don't have the trigonal symmetry anymore. You mean then it would become orthorhombic, or you would have some distortion? Yeah.
Right.
Yeah, but
I understood that the normal states are sometimes isotropic. Right. So so in those cases, if you're saying anisotropy, which is not the naive crystal symmetry, I mean, you look it up and it says it's orthorhombic.
Yeah, but it's not because the crystal structure. It's not that there is a distortion. It's not like in the pnictides, where nematicity is more used in relation to going from tetragonal to orthorhombic. So you have already a distortion in the crystal structure, and then the superconductivity follows. So here it is actually something that happens in the electron liquid, so not in the crystal structure itself. But you cannot exclude that this is also present already in a normal state, but then you should find a reason why it is there. It's a puzzle.
The fluctuations of if you have two component superconducting thing, the fluctuations of that could generate some anisotropy that starts with the higher temperature.
I think that's maybe this vestigial nematic order that it already happens in the. So the normal electron liquid does something, and then the superconductivity follows.
Let's say, for instance, that there was need some kind of subtle ordering or direction that was associated with impurities.
Yeah.
In the normal state, and then this was reflected in just kind of almost purely normal state property, like this is sitting.
Yeah.
Then you cool it down to normal state, and this.
Yeah, I think therefore we would need to know better where the strontium atoms sit.
Yes, thanks for continuing work on this. Almost everybody else are giving up, but yeah, wonderful survey. For the sodium compound, may I clarify a little bit? I didn't follow the literature, of course. That misfit compound is superconductor or is not superconductor?
It's also superconductor.
And
it's orthorhombic. It has orthorhombic and it has an anisotropy.
I see, and then same TC. Wonderful, thanks.
So really nice talk. I'm back here. Hi. I have a quick question about maybe it's beside the point, but I mean, even very early on, I showed the ARPES data. It looks like the Dirac point is like 300, 400 millivolts below the Fermi level.
Correct. Yeah.
So,
But that's normal for bismuth 2 selenium 3.
right, but I mean, so I guess I'm having a little bit of a hard time understanding whether the Dirac physics then should be necessarily relevant to what's going on here, or is it just sort of, you know, kind of ancillary, and what you're seeing here is really kind of distinct from that.
In this paper by Fu and Berg, so it relates to the symmetry of the system. And so if you have this time reversal symmetry and inversion symmetry, then you can have this topological superconducting state under certain conditions. And then you can make, if you take into account the orbital momentum and the spin momentum, and you make the symmetry table, then you get these topological superconducting states. So it follows from there. But the real topological properties are on the surface.
Well, I think it's a question as to if you get a topological superconductor in a doped topological insulator, there's two completely different things that can happen, right? It might be that the topological insulator it's there because you have strong spin orbit coupling, and then when you get pairing in the bulk, you're actually getting a topological superfluid in the bulk with may around the surface phase have nothing to do.
It's the Dirac cone of the bismuth 2 selenium 3, which actually gives the special properties. It's just the material itself. So this Dirac cone should also be gapped.
Okay, last quick question.
In the paper by Van der Bos and Fu, they predicted, well, they considered two other parameters, two combinations, delta for x, delta for y. One was supposed to have nodes, the other fully gapped. So experimental question, has there been any thermal conductivity measurement specifically in plane to see where the nodes are?
Yeah, I think we very much would like to do such type of experiments, but the problem is with purity of these materials, so like the residual resistance ratio is not very good for these materials. Yeah, and superconducting volume fractions are always somewhat limited. So then you thermal conductivity, any experiment you want to do, yeah, it's very difficult to see. Penetration depth measurements have been done, but it's very difficult to interpret.
Okay, let's thank Anna again. Section, Matt Foster for Bryce, will tell us about spectrum-wide quantum criticality.